Hello everyone, we are here with a new training course, Heat Transfer course. This session is an introduction to the topics and points of heat transfer simulation. As you may know, heat is transferred via solid material, conduction, liquids and gases, convection, and electromagnetic waves, radiation. Heat is usually transferred in a combination of these three types and randomly occurs on its own. As a result, it is important to understand those three phenomena taken separately. For example, in this picture, we have three types of heat transfer. As can be seen, from the windows of the room, we have convection heat transfer where cold air enters, and in the part where there is a fireplace, the air heats up and then goes up. From the floor where we place the heat source, conduction is down in solids and radiation heat transfer has taken place next to it. Note that in this course, I don't talk about radiation and I just talk about conduction and convection heat transfer. Convection or convective heat transfer is the transfer of heat from one place to another due to the movement of fluid. Although often discussed as a distinct method of heat transfer, convective heat transfer involves the combined processes of conduction, heat diffusion, and advection, heat transfer by bulk fluid flow. Convection is usually the dominant form of heat transfer in liquids and gases. Note that this definition of convection is only applicable in heat transfer and thermodynamic context. It should not to be confused with the dynamic fluid phenomenon of convection, which is typically referred to as natural convection in thermodynamic context, in order to distinguish the two. Two types of convective heat transfer may be distinguished: free or natural convection and forced convection. Mixed convection is another type, and it is a combination of natural convection and forced convection. Natural convection, also known as free convection, is a mechanism or type of mass and heat transport in which the fluid motion is generated only by density differences in the fluid occurring due to the temperature gradients, not by any external source like a pump, fan, suction device, and etc. Actually, when fluid motion is caused by buoyancy forces that result from the density variations due to the variations of thermal temperature in the fluid, this kind of convections will be occurred. In the absence of an internal source, when the fluid is in contact with a hot surface, its molecules separate and scatter, causing the fluid to be less dense. As a consequence, the fluid is displaced while the cooler fluid gets denser and the fluid sinks. Thus, the hotter volume transfers heat towards the cooler volume of that fluid. Buoyancy is what drives natural convection, where the pressure differential between air heated by heat sources and surrounding ambient air drives the hot air upwards and away from the heat source. The air rises up with the energy it absorbed and thus removes that energy from the area around the heat sources. Forced convection is convection in which the movement of fluid doesn't happen naturally but is helped by a device such as a fan or pump. Actually, this kind of convection occurred when a fluid is forced to flow over the surface by an internal source, such as fans, by string and pumps, creating an artificially induced convection current. And about mixed convection. Actually, combined forced convection and natural convection or mixed convection occurs when natural convection and forced convection act together to transfer heat. This is also defined as situations where both pressure forces and buoyancy forces interact. And about mixed convection. Actually, combined forced convection and natural convection or mixed convection occurs when natural convection and forced convection act together to transfer heat. This is also defined as situations where both pressure forces and buoyant forces interact. In the study of heat transfer, Newton's law of cooling is a physical law which states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its environment. Actually, the law is frequently qualified to include the condition that the temperature difference is small and the nature of heat transfer mechanism remains the same. As such, it is equivalent to a statement that the heat transfer coefficient, which mediates between heat losses and temperature differences, is a constant. This condition is generally met in heat conduction, as the thermal conductivity of most materials is only weakly dependent on temperature. In convective heat transfer, Newton's law is followed for forced air or pumped fluid cooling, where the properties of the fluid don't vary strongly with temperature, but it is only approximately true for buoyancy-driven convection, where the velocity of the flow increases with temperature difference. Finally, in the case of heat transfer by thermal radiation, Newton's law of cooling holds only for very small temperature differences. In heat transfer simulations, there are some non-dimensional numbers that I want to explain them now. In fluid mechanics, especially fluid thermodynamics, the Grashof number is a dimensionless number which approximates the ratio of the buoyant to viscous forces acting on a fluid. It frequently arises in the study of situations involving natural convection and is analogous to the Reynolds number. Free convection is caused by a change in density of a fluid due to a temperature change or gradient. Usually the density decreases due to an increase in temperature and causes the fluid to rise. This motion is caused by buoyancy force. The major force that resists the motion is the viscous force. The Grashof number is a way to quantify the opposing forces. In this equation, G is a gravitational acceleration. Beta is the coefficient of thermal expansion. Delta T is the temperature difference between surface temperature and bulk temperature. L is the length, and nu is the kinematic viscosity. The transition to turbulent flow occurs in the range Grashof number between 10 to the power of 8 and 10 to the power of 9 for natural convection from vertical flat plates. At higher Grashof numbers, the boundary layer is turbulent. At lower Grashof numbers, the boundary layer is laminar, that is, in the range Grashof number between 10 to the power of 3 and 10 to the power of 6. The Prandtl number is a dimensionless number defined as the ratio of the momentum diffusivity to thermal diffusivity. The Prandtl number is given as the equation here. In this equation, mu is the dynamic viscosity, K is the thermal conductivity, and Cp is the specific heat. In fluid mechanics, the Rayleigh number for a fluid is a dimensionless number associated with buoyancy-driven flow, also known as free or natural convection. It characterizes the fluid's flow regime. A value in a certain lower range denotes laminar flow, a value in a higher range turbulent flow. Below a certain critical value, there is no fluid motion and heat transfer is by conduction rather than convection. For most engineering purposes, the Rayleigh number is large, somewhere around 10 to the power of 6 to 10 to the power of 8. The Rayleigh number is defined as the product of the Grashof number, which describes the relationship between buoyancy and viscosity within a fluid, and the Prandtl number, which describes the relationship between momentum diffusivity and thermal diffusivity. Hence, it may also be viewed as the ratio of buoyancy and viscosity forces multiplied by the ratio of momentum and thermal diffusivity. note that it is closely related to the Nusselt number, and in this equation alpha is the thermal diffusivity. In thermal fluid dynamics, the Nusselt number is the ratio of convective to conductive heat transfer at a boundary in a fluid. Convection includes both advection, fluid motion and diffusion, conduction The conductive component is measured under the same conditions as the convective but for a hypothetically motionless fluid. It is a dimensionless number closely related to the fluid's Rayleigh number. A Nusselt number of value 1 represents heat transfer by pure conduction. A value between 1 and 10 is characteristic of a slug flow or laminar flow. A large Nusselt number corresponds to more active convection with turbulent flow, typically in the 100-1000 range. Note that in this equation, H is the convective heat transfer coefficient of the flow, L is the characteristic length, and K is the thermal conductivity of the fluid. Another thing that needs to be said and discussed is that in most articles related to heat transfer simulations, dimensionless numbers are used. In this slide, you can see how these numbers have become dimensionless. Most of us are familiar with the definition of boundary layer and how it is formed. And we know that when a fluid is close to a wall that has a no-slip condition, it forms a boundary layer. The boundary layer is the geometric location of points whose velocity is up to 99% of the input velocity. We also have a temperature boundary layer, which is the geometric location of points whose temperature is up to 99% of the inlet temperature. Therefore, it is better to apply the boundary layer mesh on the geometry in heat transfer simulations. Now, I want to explain some important points in heat transfer simulations. One of the important points in heat transfer simulations is about pressure discretization method. Actually, it is better to use the body force weighted method at first in this kind of simulations, and then you can use the Prandtl method. Please note that using the standard method causes wrong simulation of the velocity near the walls of the model. When doing time-dependent simulation, transient simulation, an important part to consider is the time step. The phenomenon you wanna simulate itself has a time step which is obtained according to the characteristic length, the coefficient of thermal expansion, and the maximum and minimum simulation temperature in the form of the inserted equation. There are two important points here. First, in natural convection heat transfer simulation, if convergence isn't achieved in the steady state, it is better to solve the time-dependent solution, transient solution. And second point is that in simulating natural convection, gravity must be activated in the correct direction. It is a very important point. As I said, the natural convection is due to the difference in density, and in order to be able to perform this simulation correctly in ANSYS Fluent, you must activate gravity. This causes a rho g term to be added to the momentum equation, and the rho parameter becomes rho minus rho 0. The rho that changes at any moment is calculated by Fluent, and rho 0 is the density operation. You can also remove the hydrostatic pressure head from the problem. For this, it is better to consider the operation density equal to 0. Even the Fluent software suggests doing this when the density is a function of temperature. Let's see what happens by removing the hydrostatic head. Actually, when you remove the hydrostatic head, the only difference is the static pressure. Consider a simulation that involves simulating water in a pipe. Once we take the density reference to 0, once to 1000. Where at 0, we see that we have a higher pressure in the end parts. In fact, the answers won't be different, only the type of contour display will be different for us. I said that to simulate natural convection, the density function must be temperature dependent. In ANSYS Fluent software, there are different models for density. By using all these functions, we can make our density functions dependent on temperature, but usually Boussinesq conditions is more useful than the others. These models are constant ideal gas, incompressible ideal gas, Boussinesq, polynomial, user-defined, piecewise linear, and piecewise polynomial. The reason why it is recommended to use equations that consider temperature-dependent density to simulate natural convection is that you can add volume forces to the momentum equations. If you consider the density to be constant, it is as if you have neglected volume forces. One of the widely used approximations is the use of the Boussinesq equations, which you can use to simulate natural convection. You can add volume forces to the momentum equation with this approximation. Just be careful that by using this equation, you only consider the volumetric force density dependent on temperature, and the other densities that come in the momentum equation are considered constant. For this reason, using the approximation gives much better convergence in simulation. The equation of this model comes as you can see in this slide. You need to set rho 0 and coefficient of thermal expansion in the material section of the software. Please pay attention to these 3 points. By using this model, the non-exponential terms of the momentum equation will be reduced, and as a result, it will be converged faster than other density equations. This approximation is used when the density changes are small, about 20%. This model cannot be used in simulations that use a species transport model. In the Edit Materials section of the software, you must determine the density and thermal expansion coefficient. Then, in the Operation Conditions section, you must set rho 0. Note that the gravity must be activated before that. Another approximation considered for density influenced software is the incompressible ideal gas. When you use this approximation for density, the base density is obtained using the formula you can see here. But how to adjust the variables in this formula in the software? First, in the operation condition, you set the initial pressure in the pressure section. The next parameter, which is molecular weight, must be set in the material section, which is different for each material. There is another parameter, which is our working temperature. In order to be able to use the condition of this model, we have to set the initial temperature in the operation condition. Consider a simulation involving a very hot sphere at a temperature of 540 Kelvin, which is assumed to be inside room temperature, 270 Kelvin. Here, Boussinesq cannot make a correct simulation because the velocity changes around the hot body are large. Actually, when the density changes around the hot body cause high fluid velocity, using Boussinesq approximations cannot be ideal. Also note that, of course, the convergence of the ideal incompressible ideal gas model is weaker than Boussinesq model. And the last part is related to the piecewise linear model, which is actually the functions that the Fluent software takes from the user to guess the density. Be careful that the user must identify several points and their corresponding density to the Fluent software so that the software can perform interpolation. You must set the density between the lowest and highest temperature observed in the simulation. For example, if your temperature exceeds 50 degrees, but the temperature you set is greater than 50 degrees, Fluent doesn't understand what density to consider for your simulation after 50 degrees. To benefit from Mr. CFD services, including simulation, consultation, and training, visit our website www.mr-cfd.com and contact us via info@mr-cfd.com.